Hello, warm welcome to everyone joining. Thank you for being here. Get yourself ready with a notebook, pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much just out of nowhere. And today we have a problem involving a factored polynomial. Got some questions regarding this polynomial. Remember that a polynomial is just an expression that has one or more terms, and these terms have powers on their variables. Usually we're dealing with like powers of x. And this one is already factored, so if you were to open this up, you would have to multiply, get a result, and then you would have to multiply. It'd be a little complicated. It's a fun exercise. I think you should do that, honestly. I encourage you to do that as an exercise. A little bit of additional practice. So go ahead and take a look at the different questions we have here. These types of questions are going to be important for when you get to calculus and you have to analyze functions. It's going to be helpful to analyze factors. We're also going to use the chart in order to analyze the graph, and then we'll be able to sketch a possible graph for f of x. So go ahead and pause the video, give yourself like 8 minutes or so, try to figure it out for yourself. And then when you're ready, come on back. Let's see how we do here. Alright, let's get started. Well, if we want to determine the roots of a polynomial, let's remind ourselves, what are the roots of a polynomial? The values for, in this case, x, which make the polynomial equal to 0. That's what root is. And because this is factored, we can take advantage of the zero product property, which says that if we want this entire product, x squared times 3x minus 9 times x plus 5. Am I hallucinating? Is that the right one? Yeah, x plus 5. If we're saying that this product is equal to 0, then we know at least one of its factors must be 0. So that allows us to say that means x squared equals 0 has some solutions for us. That would just be x equals 0. 3x minus 9 has some solutions for us, right? What I'm doing is setting each of these factors equal to 0. And that will leave us with x equals 3, and also x plus 5 as a factor could possibly equal 0. This gives us some solutions as well. So we'll have x equals negative 5. These are all solutions to the equation f of x equals 0. So in a sense, they make the polynomial equal to 0. They're called roots. What I want you to notice about the roots is that they each come from these factors, and these two factors don't have anything particularly special going on, but this x factor has a squared. This is going to relate to something called the multiplicity, and it'll have an effect on the values of the function near that x value of 0, but it's also going to tell us something about the way that the graph is shaped. I guess I won't just put mult, I'll put multiplicity of 2. We'll talk about what effect that has on the graph when we get to part D. Okay, so these are the roots. Now we want to determine the vertical intercept. The phrasing of that is pretty much like a y-intercept. It means the same thing as the y-intercept. Now how do we find the y-intercept? It's the easiest thing to find in the world, usually, when you have a function. You just plug in 0. Because if we're looking at a graph, it would cross the vertical axis or the y-axis whenever x equals 0. That's here at this sort of like midline there, right? So let's plug in 0, and since we know that 0 is one of the roots, we don't even really have to do any work. We know that that's going to be equal to 0. If you want to plug it in, go for it. 3 times 0 minus 9, and 0 plus 5 doesn't really matter because we have 0 times negative 9 times 5. Anything times 0 is just going to 0 out, so we already know that it's going to equal 0. That means that this graph crosses this point, 0, 0. It's pretty useful. It'll help us out. We're building up to this ability to sketch the graph, so the more information we have about the graph, the better. For example, these roots here, these are going to be equivalent to X-intercepts. So we have the X-intercepts, we have a Y-intercept. Now let's talk about the end behavior. So the end behavior of a polynomial is very easy to determine. It's controlled by two things. What are those two things? It's controlled by the degree, whether it's even or odd, and it's controlled by the leading coefficient, whether it's positive or negative. Just understanding this about the polynomial is going to give you all the insight you need to understand the end behavior, like what's happening all the way to the right and all the way to the left. The idea here is that if the degree is even, then either both sides are going to go up or both sides are going to go down, and this is going to depend on the leading coefficient. So if the leading coefficient is negative, it's going to make both sides of that graph go down. And if we have odd degree, pretty much means they don't agree. So we'll have up to the right and down to the left, or if the leading coefficient is negative, we'll have up to the left and down to the right. The reason why there's this space in between is because I don't know what's happening in the middle of the graph necessarily, but I do know that at the ends, all the way on the right and all the way on the left, I know whether it's going up or down. And so let's take a look at our polynomial. What degree is this? Well, I told you don't have to multiply everything out. But if you would multiply everything out, if you did, you would end up with a bunch of terms that you have to combine like terms and simplify. But you would still end up with a bunch of terms being added together. And the first leading term would be made up of all of the leading terms in the factors. So at some point, what I'm saying here is that at some point we would have multiplied the x squared to the 3x, and then at some point we would have multiplied that to the x. Right, we would have multiplied this, and then at some point we would have multiplied that product onto the x. There are other things going on as well, but that's what's going to produce the highest power of x. So we can tell that 3x to the 4th is going to be the highest term. So this is even degree with positive coefficient. So that means that we're going to have end behavior which looks something like this. On both sides, the graph is going upwards. I don't know that the middle is necessarily at x equals 0, but I'm just suggesting that at the very ends, which we write like this, as x goes to infinity, the y, or you can say f of x, I guess I'll put f of x. The y values, which are the f of x values, also go to positive infinity. And as x goes to negative infinity, where is negative infinity on the x number line? That's to the left. So basically I'm saying as we go left, f of x is also going to positive infinity still. Notice how it's still going up. That's the rule. Okay, great. Let's move on to the multiplicity. And using, not the chart, it's just the chart. There we go. And we're going to sketch the graph with the help of the chart and the help of multiplicity. If you haven't seen my video on the chart, it is one of the most useful things for analyzing functions. You'll be using this a lot in calculus, even though it's most likely that your teacher will not teach it to you. So go take a look at my video. I'll put the link in the description for the chart, and we'll see how to use it. First, let's talk about this multiplicity thing. So what does multiplicity exactly tell us? It counts the number of, let's make this smaller. It counts the number of, let's say, repetitions of a root. It's like represents a repeated root, and it's indicated by an exponent and a factor for that root. So what I'm saying here is the root that we had, x equals 3, it had a factor of 3x minus 9, which indicated that root. But that factor didn't have a special exponent like a 3 or a 4 or anything. It just had nothing, which we assume means there's a 1 there. Because of this, we have a multiplicity of 1. Roots with an odd multiplicity cross through the x-axis according to their exponent behavior. So because the multiplicity is 1, this is going to act like a linear factor that goes through the x-axis. So at x equals 3, I know that it's either going through upwards or it's going through downwards, but it's going through the x-axis there. In fact, I'm going to put it on the graph. I might as well represent it there. Here we have 0. And what was the other root that we have? We had -5. Now, I already know what's going to happen on the ends. So if I wanted to sketch this from here, I actually could do a decent job at sketching it from here. But I want to show you something special because the root x equals 0, which is associated to the factor x squared, we mentioned that has multiplicity 2. And I want to mention what happens when we have roots with an even multiplicity. Bounce off the x-axis. That's just always the rule. It bounces off. I don't think I even needed another line for that. There we are. So what that means is that these ones go through either like that, or like that, like that, or like that. You see how they're going through the x-axis? The x equals 0 root is going to either bounce or it's going to bounce, something like that. Okay, it's not going to pass through the x-axis. It's going to bounce somehow. Okay, great. Now let's represent the factors on the chart. So the chart has the number line along the top with our important x values. In this case, our roots are going to be represented here. And we have our factors, x squared, 3x minus 9, x plus 5, and then at the very bottom we have the product, which is f of x. That's the product of all of these. So you know how to use the chart. Put a 0 here at the corresponding x values for each factor, and then we just do the pattern. But you have to notice that x squared has a special pattern. X squared is always positive unless it's 0. I should say it's never negative, right? Because any number squared is going to be positive. Now for these linear factors, we just do the normal pattern. Negative on the left, positive on the right, negative on the left, positive on the right. And then for the product, which is the final row on the bottom, we're going to write our zeros because if any of the factors equals 0, then for sure we're going to get 0 in the product that's given. Then on the left side of -5, we have a positive times a negative times a negative. That's positive. Then we have the 0. Then we have a positive times a negative times a positive. That's a negative. Then on the other side of the 0, again, we have a positive times a negative times a positive. Still negative product. And then on the right side, we have all positive factors. So of course the product is positive. And this shows us the positive and negative behavior of the function. See how it goes positive, 0, negative, 0, stays negative. That's indicating our bounce X-intercept, our bouncing root. And then we have 0 and positive again. So I could have predicted the outsides already, that the left and right sides would be positive since we know the end behavior. There we go. And these are just sketches. We don't have any specific points on here. We don't really know when the turning points are, for example. That would require calculus for us to analyze that a little bit more carefully. But I know that roughly it's going to go like downwards and then bounce somehow and then like come back up. So like I said, calculus would show you how far down it actually goes. I don't know if it goes that far down or if it goes like that far down and then comes back. We don't really know unless we use calculus, but we have a decent sketch of what's happening with the graph, right? We have this going negative, bounces at 0, and then it goes negative again. By the way, this bouncing spot, it is smooth. It's not going to be pointy. It's not a sharp corner. It's going to be like a hill, like a nice hill, not a cliff. Okay? And that gives us our sketch of the function. If you want to plug in any values and get specific, more accurate points, then you can feel free to plug in certain x values, like x equals 1, x equals 2, and you can get some more accurate values. But I think that's enough blab out of me. Hope you guys learned something about using the chart, and I will see you next time.